Good morning, ladies and gentlemen. Mr. Eicher here to teach you about sequences as functions, Chapter 9, Section 1. In the previous lesson, we learned about recursive formulas, so we're going to review that a little bit today. Also talk about domain and range, which we've talked about throughout the course. But let's just start with this sequence that we're provided. See if you could figure out the next terms in the sequence. Remember, a sequence is a set of numbers in a particular order. So there's some pattern here. So you probably guessed it. It looks like the next number is 12 fifths, 10 fifths, and 8 fifths. So each number we're subtracting by 2 fifths. Or you can think we're adding negative 2 fifths to get to the next term. This one right here, yes, that's true. You could write as 2. We probably should simplify it as 2. The others we'll just leave as improper fractions. So what would a recursive formula look like? Well, with a recursive formula, you say where you begin. So a sub 1 is our starting point. That's the value 18 fifths. And then you explain how you get any value, a sub n, any nth value, whether it's the n is 5, that would be the fifth value. N is 25, that would be the 25th value. So to get any value, you take the term before it, which is a subscript n minus 1, that's the term before it. And then we just said we're subtracting 2 fifths each time, so minus 2 fifths. And that would be our recursive formula. This would be defined for n's. I'll write it right here. For n's greater than or equal to 1. We wouldn't use this value to find some, like, what's the negative fifth term in our sequence. But we would find it to find our first, our second, our third, our fourth. And that idea is related to the domain and range, which we'll talk about in a second. But I just wanted to show you, so for instance, if you wanted the second term, you would take the first term minus 2 fifths. And the first term was 18 fifths. You'd subtract 2 fifths. And so our second term, a sub 2 is our second term, is 16 fifths. Okay, and then lastly, for our domain and range, our domain is the set of natural numbers. It's the set of natural numbers because, like we said right here, n's greater than or equal to 1. That means our domain is 1, 2, 3. Those are the first 3 terms we were given, and then we found the 3 terms after that, so 4, 5, 6. So our domain are the natural numbers from 1 to 6. Again, the domain is basically what position we're on, so the first, the second, the third, the fourth, the fifth number, the sixth number. And then the range, run out of space here, so I'll write it down here. The range are the values themselves in our sequence. So 18 fifths, 16 fifths, 14 fifths, 12 fifths, 2, which was 10 fifths, and then 8 fifths. And I'm using brace. Brace is their set builder notation. So our domain are the positions that we're on, the first position, the second, third, fourth, fifth, sixth, and then our range are the actual values of the sequence. Alright, so a couple terms to recap what we were just doing. We were working with a sequence. Sequence is a list of numbers in a particular order. These numbers were in a particular order. Each number is called a term. That was, we found the next 3 terms, so numbers are called terms. The first term, the notation for the first term is typically an A with a subscript 1. The notation for the second term is a with a subscript 2, and etc., etc. The next term in the sequence, we could use the notation a and then n plus 1. The previous term is the notation a sub n minus 1. So if you're on the fifth term, if you want to go backwards, you'd subtract 1 from 5 and you get 4, so the fourth term. And then the last term, if there are n terms, is a sub n. The most common ones that we'll use in this chapter is the first term and the last term are the really important ones, but you'll see this one a lot too with recursive formulas. In this column over here, I just wanted to note that most of the time we use a sub 1 for the first term, but occasionally, like in yesterday's lesson, we actually used a sub 0 as kind of our starting point, or our first term. So it gets a little tricky there because we might refer to this as the first term, even though there's a subscript of 0 and not a 1. So if the first term, if this is defined as the first term, then the second term would actually be 1 more than 0, so a sub 1 would be the second term. So I just include those so you're aware. Most of the time, though, we'll be using this left side, these symbols in notation. And then let's see, we have the last term's a sub n. If the sequence is infinite, then you'll see a dot 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 at the end of the sequence. So if we wanted a sequence that's infinite, we just put the dot 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 there, and that means it goes on. The pattern continues infinitely. So that means this one right above, if there is a last term, then we call this a finite sequence. It has an ending point. It is not infinite, where it doesn't have an ending point. And a sequence, last part here, a sequence is a function in which the domain consists of typically natural numbers. If we start with 0, it would be whole numbers, but typically we have natural numbers for the domain of a sequence. And then I can't really see it on the screen, but I think it says in the range. Oh, there it is. And the range consists of real numbers. Now, this doesn't mean that we use all real numbers or that we use all natural numbers. If it's a finite sequence, then we just have some natural numbers and some real numbers. So those are sequences in general. In this chapter, we'll learn 2 sequences. In this chapter, we'll learn about what are called arithmetic, or arithmetic, but I usually say arithmetic. We'll learn about arithmetic sequences, and we'll learn about geometric sequences. So in this very lesson, we'll learn 2 special type of sequences that are related to some other things in mathematics. So an arithmetic sequence we've kind of already seen before. The example above with the 18 fifths, 16 fifths, 14 fifths. That was an arithmetic sequence. So an arithmetic sequence is a sequence in which you add some constant value to each previous term. This constant value is called a common difference. And the letter that we use for a common difference is D for difference. So which of the following sequences are arithmetic? If they are arithmetic, what's the common difference? So let's see. In this first example, it looks like we're subtracting 4, and then subtracting 4 again. It's promising. And then finally subtracting 4, and it is infinite. Not that that matters here, but that dot 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 means that it's an infinite series. So this is arithmetic, and our common difference is -4. We're adding a -4 each time. How about pause this video and see if you could do 3, 4, 5. So pause this video, do 3, 4, 5, and I will have the answers posted momentarily. Alright, on number 4, I found a difference of adding 6, then adding 7, then adding 8, then adding 9. That is a pattern, but it's not arithmetic. It needs to be a constant difference. No constant difference. Constant difference. So it is not arithmetic. Number 4, I did find a constant difference of 9, d equals 9, so that is arithmetic. And then on number 5, we got 4, difference of 3, difference of... Oh, I think my numbers changed. So on 5, those should be the right numbers now. On 5 I got a 4, a 3, a 3, a 3. It's almost a common difference, but we would say that is not arithmetic. It needs to have a constant difference from one term to the next for all the terms. Thank you for watching this video. We'll continue number 6 in the next video.